We have now learned what's happened when the function is analytic in some disk. The whole disk consisting of a center set 0 with radius r0. Now we are going to consider a more general situation when the function is analytic in some ring region like this. It's given by two radiuses r1 and r2. We have two disks, the larger disk with the same center as the smaller disk has radius r2, and the smaller disk has radius r1. And we are going to assume that the function is analytic in the region, the ring region between these two circles. Then we have the following theorem or result given by Laurent, which is called Laurent Theorem. And it states that the function f can be represented as the sum of two infinite series. The first series looks like the one in the Taylor theorem. It has the same symbol for the coefficients an, and n is going from 0 to infinity. And we also have some other terms here, the bn terms. Bn is multiplied with set minus set 0 to the power of minus n, and n is going from 1 to infinity. Now, these two types of coefficients, an and bn, are given by the following more complicated expressions. An is just 1 divided by 2 pi I multiplied with the integral of over some curve C. And the curve C is any curve positively oriented closed curve which is going like this. Starts anywhere in the region between these two circles and goes around the inner circle. And these integrals are given as follows. It's the integral of the function f of z, which is analytic in the ring region, over z minus z0 to the power of n plus 1. So this is the an coefficient, and the bn coefficient is equal to 1 over 2 pi I times the integral over c of the function f of z over z minus z0 to the power of minus n plus 1. We can derive the Taylor theorem for the special case when f of z is analytic inside the inner circle as well. And we know that in order to see this, we use the Cauchy integral formula, which you have seen before. It states that if the function is analytic in z0, then it can the nth derivative of the function of z0 is equal to the faculty of n over 2 pi I times the integral over c of the function f of z over z minus z0 to the power of n plus 1. So this is the Cauchy integral formula. And by dividing each side by the faculty of n, we obtain the following expression. And this expression is exactly equal now to the coefficient an. So this is the definition of these an coefficients in the Laurent theorem, which was given by this expression. So therefore we know that an now is equal to the nth derivative of z0 over n faculty, the faculty of n. And this is exactly the coefficients in the Taylor theorem. So the only thing we need to know is that the Bn coefficients are 0 when the function f is analytic inside the larger circle. But in this case we have that well, this is just the expression for Bn in the Laurent theorem, and we note that we may replace this denominator. We could just replace this by z minus z0 to the power of n minus 1. It's easy to see because we just take the negative exponent and put it into the denominator. But now we know that this function f of z is analytic, and z minus z0 to the power of n minus 1, this is just a polynomial function multiplied with the function f of z. So these two functions must be analytic separately, and the product of analytic functions are also analytic. So therefore this function is analytic interior to the curve C, the closed curve C. But then we have from the Cauchy's theorem that the integral, closed integral, should be equal to 0, because this function is just analytic. So therefore the coefficients Bn are equal to 0 for any n. And summing up, we find that the function f of z is equal to this expression, which is exactly the Taylor series.